Hello friends and welcome to the fourth part of this video tutorial series on molecular dynamics. In previous video we have solved some examples using Beeman's algorithm, and in this part we will see how to code this Boris algorithm, and lastly we will see some applications of this molecular dynamics. So let's start with this Boris algorithm. So this method is an excellent method to solve Lorentz force equation, and as given on this Wikipedia page of Lorentz force, this is the expression for Lorentz force: Q times E plus V cross B. E is the electric field, V is the velocity of particle, and B is the magnetic field. Must notice that this is the velocity dependent force, and this set of equations represents the Boris scheme. I have taken this equations from this Wikipedia page of particle in a cell, and down here you will find this equation. These are the same equations which you can see here, right? Now you might have noticed in this subscript of this velocity term they have written Vk plus 1/2. Here k is an integer, means 1, 2, 3. That is not a big problem. But what is this 1/2? So answer is this 1/2 represents the half velocity. And how we can find this half velocity? Answer is here. Initially, instead of taking this delta t as in time step, we will take delta t divided by 2 as a time step, so that we can find v1/2. And then in first epoch we will again consider delta t as a time step, so we will have v1 plus 1/2. You can easily replace this 1 with this k for kth epoch. So this is the kind of a generalization. So I think we are ready to code this Boris algorithm. So let's jump to the code now. Let me maximize this window so that you can see. So this is the code, and this is Mr. Dynamics object. As I said in first video, this Mr. Dynamics will solve our problem, and this is the first part of Mr. Dynamics, means initialization. Then comes the heart of Mr. Dynamics, means algorithm part, and this is the third optional plotting part. Let's look closely to this second part, which is our Boris algorithm. First of all, I am unpacking my variables. From this small r, I am unpacking x, y and z position. From this v, I am unpacking vx, vy and vz velocity, and same goes for electric field and magnetic field. Then comes the initialization part, means step 1. Here I am using Euler-Kromer method to initialize my Boris algorithm. Must notice that instead of taking delta t, I am using delta t divided by 2 as a time step. Okay, this completes the step 1. We are ready for step 2. This step 2 is our Boris algorithm. So we are done with the initialization, and this is the Boris algorithm. Here this h, s, u, u dash, all this variable you can notice here. This is my u dash, this is u, this is h, and this is s. I am doing it manually. You can write function cross prod to do this cross product, but personally I found it very difficult. So what I have done is I have expanded this formula, means this big formula, and code it. Okay, so this is the position update, and to keep a record of my position, I am appending this x, y and z variable to the list of x, list of y and list of z, which I have defined in this initialization part. This completes the second step, and we are jumping on to the step 3, means velocity part. See, we have calculated half velocity. As you can see here, this is not v1, this is v1 plus 1 half, and similarly for in next epoch we will have v2 plus 1 half. So this is not full velocity, right? But for analysis purpose we need full velocity. So here's the trick I am using. As I mentioned, as I have discussed in second part of this series, I will use this equation, means position I plus 2 minus position I divided by 2 delta t, means from this list of position I will calculate velocity, right? There are several ways to convert this half velocity into full velocity, but this is personally this is my favorite, so I'm using this method, right? So this completes the second part, means this algorithm part. Let's pass some arguments to this object and run this code. So this is the charge of particle, this is the mass of particle. Initially my particle is at origin, and I am applying 10 Tesla magnetic field in z direction, means in vertical direction, and this is the velocity component. So this is the x component of velocity. So this x component of velocity is perpendicular to this magnetic field. This will give rise to a kind of a rotation of charged particle, and here is this second component, means a z component of velocity. This will give rise to a vertical shift, right? So if we combine this rotational motion and linear motion in z direction, we can expect a kind of a spiral like pattern as an output. So let's pass all these arguments to our object Mr. Dynamics and see what we are getting. Let's run this thing, and yes, so this is the result. As I said, we are getting and kind of a spiral shape as an output. This is the z direction, this is x direction, and this is y direction. These three are the phase plot. Phase plot means position coordinate on horizontal axis and velocity coordinate on vertical axis. So this is for x component, this is for y component, and this is for z component. So this completes the Boris algorithm. Let's jump to the presentation now. Before we go to the application part, here is the brain map. So if you have any kind of force, first thing you do is classify it. First classification is check that if it is velocity independent force or velocity dependent force. If it is velocity independent force, then you can use these four algorithms: Euler-Kromer, Verlet algorithm, velocity Verlet, and Biemann's algorithm. In this course, I haven't covered this velocity Verlet algorithm. If your force is velocity dependent, then further ask if magnetic field is present or it is not present. Means here, if magnetic field is not present, then go for Euler-Kromer method. If magnetic field is present, then you can have Euler-Kromer and Boris algorithm. Notice that in all categories you can use Euler-Kromer method, but here's the catch: accuracy of your result is going to be poor one. So that's why you must go for this Biemann's algorithm or Boris algorithm when you have these categories. Let's look at some of the application of molecular dynamics. So the first application is my favorite. We can use this molecular dynamics for physics education, so that student can visualize different forces acting on particle very easily. The next is plasma physics. As I said, we can use Boris algorithm for plasma physics, and personally I have used this Boris algorithm for my final year project. The next is to simulate biomolecules, to study the solid state physics, medicines, and that kind of things you can do with molecular dynamics. So this completes the last part of this tutorial series. Thank you for your attention. See you guys in the next video. Bye.